Hello everyone. In this video we are going to talk about the construction of Green's function for forced linear oscillator. If you're not familiar with Green's function construction, don't worry, we'll be talking about that in this video. But also I want to give a shout out to a playlist in my channel which is on Green's function, so I'll be linking them in the description. So make sure you find that out and solidify your knowledge on construction of Green's function. Let's go on with the video. So first, what we need to ask ourselves is, why do we need the Green's function procedure? Well, it's because for any linear inhomogeneous differential equation, knowing the Green's function tantamounts to solving the differential equation itself. So if you have a linear homogeneous differential equation, that means there is no source term, as we'll see within a minute. What you need to do is to find out n independent solutions, where n is the highest derivative in that differential equation. It's also called the order of the differential equation. So you have all those, so those are homogeneous solution, and then you have something called the particular solution, which is the most important part in our solution of an inhomogeneous differential equation, because that extra part, particular solution, arises due to the inhomogeneity, that means the source term in the differential equation. For simplicity, the source term is a term which is only a function of the parameter. For example, in mechanical problems, it's going to be the time. But it's not, the term does not contain any independent variable. So the function whose solution we're going to find will be the dependent variable, and that isn't contained in the source term. So, for example, here in equation number 1, we have written a differential equation. It doesn't look as such, but remember, here we have written it in an operator format. So this L, this curly L here, it denotes the differential operator. So it contains the derivatives. And that acts on this function x of t, which is presumably the solution we are trying to find. And L of x is going to be the left-hand side of the differential equation. On the right-hand side, we have the source function, which is denoted by f of t. Notice it does not contain any x in it. It's only a function of t, and we have imposed no other condition on f, except for the fact that it's probably finite and it's not too bad behaved. That means at best it's piecewise continuous. There might be some discontinuity, but nonetheless it is an input function, and that is the term which is responsible for the particular solution of the differential equation. Now, if we do have a differential equation like that, then associated with it there is an auxiliary equation where the source term is substituted with a Dirac delta term. If you're not familiar with the Dirac delta term, it means that the right-hand side is 0 whenever t is different from t prime, and whenever t is equal to t prime, that right-hand side becomes infinity. So in equation number 1, whenever we substitute the source term, the f of t, with a delta function, then the solution of 1 would be the Green's function itself. And there is a very good reason for it, because if we know the response to the delta function, then we can construct the response to any arbitrary, well-behaved input function or source term for that matter, which justifies the previous statement, which is the knowledge of the Green's function amounts to the knowledge of the solution to the differential equation itself. So in our differential equation, which was the equation number 1, the f of t was the source term. So the interpretation of the Green's function, as we have just discussed, becomes therefore that it is the solution or response to a single impulse. And then we can write down the solution itself with the help of the Green's function, which is basically multiplying the source term with the Green's function and then integrating over the dummy variable t prime, and that leaves our solution for any desired input f of t. Now, The limits in the solution that we've just seen are deliberately omitted because they are determined by the initial conditions. In typical textbook or in typical text, you'll see the limits are in general taken to be from negative infinity to infinity. But the appropriate thing to do is to take the limit from whenever the solution started, typically from negative infinity to the current time t, because at the end of the day, we need to find out the solution as a function of t. And that is what we are going to see in the current construction of Green's function. Now, we can substitute our supposed solution into our equation number 1 in order to check the compatibility, that is, whether the solution 3 has the proper form. So that's what we have done. We have inserted the solution x of t, or supposed solution, into the left-hand side of the differential equation, and what we need to find is the right-hand side as a result. So instead of x of t, we substitute integral of g and multiplied with f, and then being integrated over t prime. And we know that L is an operator, a differential operator that acts with respect to t, not t prime. So that gets inserted into the differential equation because the integral is over t prime. And as we can see here, L acting on g, according to the definition of the Green's function, should simply produce the Dirac delta function. We replace that in here, and therefore when we take the integral over the Dirac delta function, what it does is to substitute the t prime with t, which it does in here, so we get the right hand side, which is f of t, as we have desired. So there is nothing new in this part of our story, and you notice that we didn't need the non-homogeneous part for this portion, right, as expected. Now the new part comes in the construction of the particular solution, which at least understandably and intuitively should depend on the non-homogeneous part, that is f of t, and that goes without saying. So now, in order to construct the Green's function, that is the response to the delta impulse, what we'll have to do is to introduce two discontinuous idealized functions. The first function is called the step function, or this is also called the Heaviside function. Heaviside function. And the reason is simple. Well, Heaviside is probably the first user of this function, probably not, I'm not sure about the history, but it's called the step function because it literally looks like a step, right, like this. And often this is written with a uppercase theta, so that's the uppercase theta. Sometimes it's also written with an H in order to signify Heaviside, right? We're just going along with this notation, and this is equal to, so since it's like a step, before t coincides with the value t naught, the value of the function is 0, so this is before t coincides with t naught. After t coincides with t naught, this has a constant value, let's call it a. In our definition, we'll choose this to be the unit step function, so the value of a will be 1. We'll reserve this notation of a for something else, and so it will be called a unit step function, but nonetheless we'll just call it a step function. So let's say this is a coordinate, alright, so that's the functional value axis, this is the x-axis or t-axis for us. So what happens is, assume that this point is t naught, and this is the t-axis, and this is the functional value theta, and this is the value 1, Alright? So before the value t0, the value of the function is 0, and after it reaches t0, its value is 1 and remains so throughout the rest of the values for t. So right at t equal to 0, you can see a discontinuity, and that's why this is why we call this an idealized function. The function contains a discontinuity at a certain point, and this discontinuity is crucial for us because that's what makes this function useful. This is a sudden jump from one constant value of the function to another constant value. And those of you who are familiar with the delta function and its integral, you'll notice that if you differentiate this step function or the Heaviside function, so if you take the derivative with respect to t, you get the delta function, t minus t. And this is understandable. Why? Because, well, after t0, it's a constant. The functional value is a constant, so therefore it's 0 everywhere after t0, and before t0 it's also 0 because, again, its functional value is a constant. So we know that delta function is 0 everywhere, but right at t equals t0, the function goes through a sudden jump, and so the rate of change is infinity, which is exactly coinciding with the definition of delta function, and that's why this identity holds. Okay, so the second kind of function we need to talk about is called the impulse function, and we shall be writing with an I. So I has 3 arguments. So one would be t, and the other 2 would be t0 and t1. Alright, and this shall be defined. Again, we take it to be the unit impulse. So before time t0, it's 0, and after time t1, this is 0. And remember, we are assuming that t0 is greater than t1, and it is manifested in the middle section. So before t0 it's 0, after t0 it's 0, but during in the middle, so t0 greater than t, less than t, and less than t1, here it has the value 1. So how does it look like, and what is the relation of the impulse function and the step function? Let me first make a little bit of room like that, so we can immediately write the relation between the impulse function. So the step function is supposed to be 1 after t0 throughout the rest of the values of t, but as we can see, that doesn't happen. So that means you have to subtract another step function. So once it goes step up, it has to come down again. So that's why we can establish this relationship. So I of t, t0, t1, this can be written as the step function at t0 that jumps at t0 minus the step function that jumps at t1. And the way we can see it is very simple. So let me add another point on the t-axis. So let me call it t1. So what happens is that before t1, the first function gets to jump, and during t1, the second function jumps, but in the other way around. So before t0, both of these functions are 0, right? Like that. in between t0 and t1, the first function is 1, but the second function is 0. And after t0, both functions are 1, but one is subtracted from the other. So it goes like this. So step function goes like that, and impulse function goes like this. Step function has the discontinuity at one point, whereas the impulse function has discontinuities, two discontinuities at two different points. And they're very useful, they're often used, and if you want to keep the area in between constant, so that means instead of the height 1, you have the height a, and the width remains t0 minus t1 minus t0, excuse me. So this is an area. So if you want to keep it a constant, what you can do is to take the limit in such a way, so limit t1 gets to t0, but the area remains constant. I'm speaking intuitively, of course. So this a is not just a constant, it becomes a function of t1 minus t0, because a has to change in such a way so that when you take this limit, the area remains a constant. You'll see that the function resembles more and more like the delta function. And that's why at the end of it, when you find out the response for the impulse input, so the input that looks like the impulse function, you can take similar kind of limits to get to know what is the response to the delta input, and that will be the Green's function that we're looking for. So I hope you intuitively understand the path we are following, and that's exactly what we are going to do systematically in this video. So our first step, naturally, is going to find the response to a step function. So for the step input, so that means the f of t, the external input or the source function or the non-homogeneous part, is going to be a step function. So for the step input, the differential equation is going to be, and of course there has to be jump at some point, so we'll have to have jump at t equals t0. So this can be written as x double dot, so dot means derivative in terms of t, twice beta x dot plus omega naught squared x equals a times a theta function that jumps at t equals t0. So let us try to draw a picture. So this would be the axis where we plot the function, and this is going to be the axis which represents t, the time, and before t0 the function remains 0, and after t0 the function stays at the value a. So let me label the picture. You have the functional value f of t divided by m, and this is the Heaviside function, okay, which has jumped at t0. This is the value it jumped to, which is a, so there should be an a here as well. The point at which it jumps is t0, and this axis represents t. Okay, so what it means is that the left hand side remains unchanged, of course, but on the right hand side we now have two options. One is applicable for t before t0, and the other is for t after t naught. And here this is going to be a, and before t naught is going to be 0. So before t naught, it's the equation of motion represents a homogeneous linear differential equation of second order, and of constant coefficients as well. So we have already solved that. We know the answer to that, but the impact of the change now happens at t naught rather than t equal to 0. Let us choose to supplement this problem with the initial conditions. So initial conditions, that means two mathematical conditions are to be put on for the same parametric value. This time we choose t naught, that means t0. So that means the position at t naught is going to be 0, and also the velocity at t naught is also 0. And the reason is we want our solution to start from the origin, and its effect should only be motivated by the inhomogeneous part of the equation of motion and not some pre-existing conditions. So what we can expect is that this function, this solution to the non-homogeneous equation, would be somewhat similar to the homogeneous solution, except for the fact that when the solution decays to an equilibrium, it approaches a new equilibrium, in this case the value corresponding to a. Alright? So therefore, in the limit, when t is far bigger than t naught, the particular solution should be a constant. In fact, the whole solution should be a constant. So the changing part, the variable part, the decaying oscillation should be due to the analogous part to the homogeneous solution, and then the particular part would be the constant, and together we'll have a combination of those. Now we do know the solution to the complementary part, the complementary solution, but let's now find out the particular solution, which shouldn't be too difficult because we know that it's going to be constant, and we know that it is somehow related to the value of the output, the inhomogeneous part, which is a. So based on that assumption, we should say the particular part of the solution should be a constant. Let's call it c. Now if that is the case, then look at the equation of motion. If you take the second order derivative of a constant is 0, first order derivative of a constant is 0 as well, so we better have 0 plus omega naught squared times x of p, remember we are talking about the particular solution, should be equal to a. And from here we can see xp, which is also a function of time in general, but in this case it's a constant, which we have called c, should be equal to a over omega naught squared. So we write the total solution, x of t, should be the complementary solution, which is the exponential decaying factor e to the negative beta t, but this time instead of t you must have t minus t naught, because remember the jump takes place at t naught, and all the time dependence should similarly be translated to t minus t naught. So a 1 cosine of omega 1 t minus t naught. Remember omega 1 squared is omega naught squared minus beta squared, right? Previously we have written this explicitly, but right now let us just use the shorthand notation, plus a2 sine of omega 1 times t minus t naught. Actually, we should put on another bracket around the whole argument of the cosine. So this is the complementary part, and then we should have the particular solution, which is a divided by omega naught squared. Now we need to find out the explicit values of the integral constants, namely a1 and a2, and it's the initial conditions that are going to help us to determine those values for a1 and a2. So applying the initial conditions, let's just write in short, ICs. The first one tells us that x at t naught should be equal to 0. So what do we get here? We get e to the negative 0, because t equals t naught implies that the exponent here should be set 0, so that's just 1. The exponential decaying factor is just 1. And inside the brackets, what do we have? We have a1, then cosine of 0, that's just 1. And then the next term is sine of 0, well, that's 0. And then plus a divided by omega naught squared. And that tells us that the value of a1 should be negative a divided by omega naught squared. Okay, so that's one down. Let's go for the next one, which is x dot at t naught should be equal to 0. So first what we'll have to do is to take the derivative. So you notice in the beginning we have two separate time dependent portions. One is the exponential factor, so that is basically negative beta times e to the negative beta t minus t naught. Then we have the internal quantities, right? You know, I can just copy them. That's what exactly I've done. Well, I may be rushing a bit. I should just take the derivative first and then substitute t equals t naught. So let me correct this. So let's not set it right to 0 right at the beginning. So let us just allow this factor to sit in here until we have finished the differentiation. Okay, so the next term, so e to the negative beta t minus t naught, let us keep this untouched, and inside we take the derivative. So what do we get? We get negative a1 and then omega 1, and then we have, instead of cosine, sine of omega 1 times t minus t naught, you know, the ordinary way of taking derivative. Then a2 omega 1 cosine of omega 1, then t minus t naught, and the last term is a constant, so when you take the derivative that contributes only 0. Once you do that, now we can just substitute or plug in t naught in the place of t and set this quantity to 0. So let me see what is the effect of that on the solution. So we have negative beta, then the exponential factor becomes 1. Remember, we have explained it before. If you set t equal to t naught, this is 0, so e to the negative 0 is e to the 0, which is 1. And then we have inside a1, because cosine 0 is 1, and then the contribution from the a2 goes away because sine of 0 is 0. So that's like the first term. What about the second term? Again, the exponential factor is just 1. So inside the square bracket we have 0 on the first place, because sine of 0 is 0. And for the second place we have a2 omega 1 times 1. And so from here, well, we can make it a bit better by just substituting the value for a1. So let's do that. So negative beta A divided by omega naught squared, and there is also a negative sign, so it becomes positive, plus we have A to omega 1. So if you want to solve this, this is very trivial. You just take it to the other side. The other side gains a negative sign, send omega 1, which is the coefficient of A2, into the denominator. So you have negative beta A divided by omega 1 omega naught squared. So these are the values, these are the solutions, A2 and for A1. Now let us take these quantities and substitute them into our solution. So therefore this is our solution. The first part is of course x for t less than t naught would be 0, right? And then x for t greater than t naught would result in, so we have a over omega squared, omega naught squared, then we have 1 minus e to the negative beta t minus t naught times cosine omega 1 times t minus t naught, put on extra parentheses, minus, so this is the contribution from A2, we have beta, and then divided by omega 1. Remember, A divided by omega naught squared, that has been factored out beforehand, times e to the negative beta t minus t naught, and then sine of omega 1 t minus t naught. So that is the solution after t minus t naught. So you can see there's also a jump in the solution as well, and that is a direct result of the discontinuity in the equation of motion. And so together they can be written in terms of a theta function, which is a step function or a Heaviside function. So since the jump occurs at t naught, it's the second expression times the step function. So together I can write them with the step function. Let me just copy it. So we have x of t. Now this is t for all time. There is no time limit, and the jump, the discontinuity is contained or will be contained in the step function. So there is the prefactor, there is the first two terms of the square bracket, there is the last term of the square bracket, and all we need is a step function which provides that desired jump at t naught. And this, ladies and gentlemen, is our desired solution, and this is the response to the step function input. Alright, so this is what we have. So that's like the first step among the 3 steps I described at the beginning. Find the response to the step function, find the response to an impulse function, and then finally find the response to a delta function. So this is the general result to find the response to a step function. So this video is already going on for too long. Let me just end the video here, and in the next video I'll start from here and I'll try to go to the end, but I'll go as far as time permits. It's likely that I'll need more time to provide a complete and elaborate solution. We'll continue on the next video.